Good evening and welcome to the Space Museum. Welcome. Today is a very special day. After the long pandemic, we can finally organize face-to-face meeting, face-to-face activity in the lecture hall of the Space Museum. Of course, today we also have some audience from the online platform. So also welcome to the online platform of the Space Museum. So today we have a very special event. First of all, I will need to thank the US Consulate General of Hong Kong and Macau to make this event successful. So today we have a very special guest, Dr. Hakeem Oluseyi, come from the United States to give us a talk on this topic, understanding the dark universe. So I talked with Dr. Oluseyi. I said that the dark thing in the world is the most, the interesting things in the universe. So people always ask us, what is the universe? What is the dark universe? What is dark energy? What is dark matter? So I think this is a very good topic for a general astronomy, general science topic. So Dr. Oluseyi is a faculty research fellow at Princeton University's Space Plasma Laboratory. And he's also a Robinson Professor at George Mason University. And previously, he was stationed at NASA headquarters, where he served as an astrophysicist and space science education manager for NASA faculty. He holds 3 degrees, 8 US patents, 4 EU patents, and also co-hosts many shows on TV, on online science program, online science festival. So today, instead of talking about the dark universe, I think we will spend some time talking about science education or anything that the audience are interested in. Then you can just raise your question after the talk. I think we will spend about 16 minutes talk for Dr. Oluseyi to tell us about the dark universe, and we will have like 30 minutes time for the questions from the audience. So if you have any questions, you can just ask Dr. Oluseyi after the talk for about like 30 minutes. And also you can look at the recorded video from our online program, because now audiences from the online platform can also review the talk for unlimited time through our online platform. So please join us to give a big hand to Dr. Oluseyi on the stage to deliver a talk on understanding the dark universe. Dr. Oluseyi, please.
Thank you. All right, thank you all for having me. Oh, let me not walk into the light. So I haven't given this talk in a long time, but I was there at the beginning. Not the beginning of dark matter, but the beginning of dark energy. In 1998, I hear that, I hear that this guy, Saul Perlmutter, had discovered that the expansion rate of the universe was accelerating, something no one expected. And I was mind blown. And I was doubly mind blown when I realized that I knew that guy. I didn't remember his name, but I remembered the guy. And so coincidentally, 4 years later, after working in Silicon Valley, I decide to return to academia and astrophysics research. And I show up for a job interview with the guy, Saul Perlmutter. And it's like, whoa, it's you. And he goes, it's you. So I began working in dark energy. Now, the big surprise is that dark energy is most of everything that exists in our universe in terms of its energy density. We didn't expect this. And the other thing we didn't expect is that most of the stuff that has positive gravity, attractive gravity, dark matter, was also not anything we expected. So the first questions are, how do we know it's there? And, what does it do? Well, in order to know it's there, we need to know about the regular matter, which is ourselves, okay? So when we look at the universe, if we start locally, here we are at the sun, and if we go out on a scale of about 10 light years, there's several stars around us, all right? As we go out on a larger scale, we see that the stars are not arranged randomly. They're actually grouped together. We're here in this thing called the Orion Spur, and then there's the Perseus arm and the Sagittarius arm. And what this is revealing is that we are all a part of this structure that we call the Milky Way galaxy. The Milky Way galaxy has about 400 billion stars, but it's so big, even though we're in it, we can only see 6,000 stars from the Earth, even though we're in a system of 400 billion. And I mean without a telescope, I mean with the naked eye, right? That's just how big space is. Because if stars are doing anything, they're putting out a lot of light. And yet, space is so big, we can only see the nearest 6,000 or so. So here is the vision that we have, the view that we have from being inside of that giant pancake disk. And so there's a lot of dust and gas, right, that makes up our galaxy. So stars are only about 4% of the mass of the galaxy. 12% of the mass of the galaxy is in this gas and stars. The other 84%, that's dark matter. So as we go out on a larger scale, out to about 100,000 light years, this is no longer accurate. We thought that the galaxy was 100,000 light years across. Now we know it's 200,000. But we have satellite galaxies. There's actually about 36 of them surrounding our galaxy. And when we go out to larger scales, we see the nearest large galaxies to us, the Andromeda Galaxy and the Triangulum Galaxy. And our galaxy is a part of a galaxy cluster. And galaxy clusters are where we find many galaxies. And here is a negative of a visible light image of nearby galaxies. And when we start talking about invisible matter, there's a lot of normal matter that is invisible to us. This is a radio view. So although you see these three galaxies here invisible, you don't see anything connecting them. In radio, you see all of this hydrogen gas that connects them. So one form of invisible matter is what we call circumgalactic medium, right? So surrounding every galaxy is a diffuse halo of hydrogen gas that can have as much matter in it as in the actual galaxy itself. When we go out to a larger scale, we see that our galaxy is part of the local group, but there are also these big clusters of galaxy nearby. And these clusters, here is a image inside of a galaxy cluster. Now remember that if you go back to our local group, it's about 2 million light years between our galaxy and the Andromeda Galaxy. You see these galaxies, this one and this one? These are each 2 million light years across themselves. So our entire local group of galaxies could fit inside of these guys. This is a star, but everything else you see here is a galaxy in that galaxy cluster. And when we look at galaxy clusters, here are the two bright ones. This is an image in X-rays. And you see all of this glowing stuff that you can't see in the visible. And this intra-cluster gas is 1 million degrees, and that's why it's emitting X-rays. But again, there is as much material in this intra-cluster gas as there is in the visible galaxies here. So we first got a hint, oh, there's material we can't see. We thought we'd found it. But remember, the amount of dark matter is more than 5 times the amount of matter. And this is about the same amount as the matter in galaxies. So, we're way off. And by the way, when it comes to the regular matter of the universe, only about 10% of it is in the galaxies. FYI. And so then we see on larger scales that the galaxy clusters cluster to create superclusters. Astronomers come up with some really complicated names, right? Cluster, supercluster. And at a scale of 100 million light years, right, we see what we call the large scale structure. But then at 1 billion light years, suddenly everything looks uniform. It's kind of like looking at the carpet at our feet, right? It looks pretty uniform. But if you were a flea, it wouldn't look very uniform to you, right? You see like, oh, there's a carpet fiber. Oh, there's nothing. Oh, another carpet fiber, right? But if you're far enough away, everything looks even. And it's because of this that we are able to do the science of cosmology, because this simplifies the mathematics so we can actually solve it. All right? Now, when Hubble was built, the Hubble Space Telescope, the guy who had guaranteed time, Bob Williams, he decided to do something that no one thought was a good idea. He decided to take the telescope and point it at a place in the sky where it appeared to be nothing. And for 10 days, just stare at that location and gather all the light that you can. And that's when we discovered that as far back as we can see, it's just galaxy after galaxy after galaxy. And so counting the number of galaxies in this tiny patch of sky, we could extrapolate and calculate that there must be around 400 billion galaxies in the entire observable universe, which sounds like a big number, but it really isn't. And I'll tell you why. I thought, okay, what is a good analogy for the galaxies in the universe? So galaxies are about 10 to 100 times their own size apart from each other. And you know what else is like that? Air molecules. They're about 10 to 100 times their size apart from each other. And so how much of a volume of air do I need to have 400 billion air molecules? It's about a cubic millimeter of air, right? So that is not very different from our universe. Our observable universe is this tiny thing, and the actual universe is something much more massive, just like the actual atmosphere is much more massive than a cubic millimeter of atmosphere. So let's get to dark matter. How do we know it's there? Well, the data that convinced us came from looking at a spiral galaxy like this. You have the center where there's a supermassive black hole, and then you have all these stars that are orbiting. So as you move from the center of the galaxy outward, you expect the speeds of the galaxies at the stars as they orbit the galaxy to become less and less. But what happens instead is they all pretty much have the same speed. And if you look at the laws of physics, one way that you can account for that is that if what we see is this, but what's really there is that, then that would give you that observation. And so we realize that galaxies are embedded in a giant halo of dark matter. But the dark matter does not collapse down to form galaxies and stars the way normal matter does. And the reason why is in the name. If you think about how a star forms, so let's say I have some piece of matter and it's coming into the gravitational well of a star and it's going to become a part of that star. Well, when it falls into that gravitational well, it gains speed. So it should come out with the same speed it went in, but it doesn't. And the reason why is because the matter has a trick for losing energy. And you're using that exact same trick right now to lose energy. And you know what that is? Emitting light. We're all emitting infrared light. So the galaxy emits light of all kinds. Dark matter does not emit light. Dark matter does not reflect light. Dark matter does not absorb light. It does not interact with light in any way. So because of that, it can't cool. And because it can't cool, it can't make compact objects. It's always big and fluffy. Now, that data I showed you about spiral galaxies was not how dark matter was first discovered. In the 1930s, a scientist named Fritz Zwicky had discovered that galaxies and clusters are moving around. And he measured how fast they were moving around each other. And he found that if you add up all the mass you have here, and that's what's holding everything together gravitationally is the mass, that there wasn't enough mass to hold the galaxy together. Based on the speeds that they are moving, all the galaxies are moving faster than the escape velocity. That means that these clusters should not exist unless there was 9 times as much matter surrounding this cluster than what we see in the galaxies. And then they would hold together. And so the third piece of evidence is what we call gravitational lensing. You see this arc right here? And you see these little arcs? Well, what's going on there is space-time is curved by the presence of matter and energy. And light and everything else that moves has to follow the shape of space-time. And so, if you have a large mass, whether it's regular matter or dark matter, and there's a distant galaxy, if the mass is lined up directly between the Earth and the object, and the mass is spherically symmetric, then the object would be stretched into a circle. If there's an asymmetric distribution of mass and perfect alignment, you get 4 images of the object, what we call an Einstein cross. This is an Einstein circle. And this, as in most cases, you have a very anisotropic distribution of mass. You get the arcs that we see. So the background, what's your name, sir? Yeah, you, Devin. So suppose, this is how it works. So Genevieve. So Devin and Genevieve, I'm perfectly lined up. I shouldn't be able to see Genevieve. She shouldn't be able to see me. But if his head was incredibly massive, does he have yeah, that works, right? Then what would happen is the light from Genevieve that's going this way would get bent by his gravity and come around. So instead of not being able to see him, I would see an image of Genevieve right here. I'd see one right there. I'd see one right there, right? And so these are actual images of actual gravitational lensing. But here's the thing. The amount of lensing that you see is related to how much matter is in the foreground. And when you calculate how much matter is necessary to give us the amount of lensing that we see, we find that it's always about 10 times more matter than we can account for. So spiral galaxies, galaxy clusters, gravitational lensing are all telling us the same story, that there's a lot of stuff there that we can't see, and it does not interact with light at all. And then when we calculate how the early universe works, it turns out that for our calculations of the nuclear physics to be consistent with what we observe, you have to have dark matter, and it must not participate in the nuclear reactions. So that's a fourth, much more complicated piece. But here again, you see galaxy lensing, right? There's a lens galaxy there, lens galaxy there. Everything you see that looks stripy is a galaxy lens. Here's another one. This is all the same galaxy image multiple times. This little weird looking one here. Yep, there's another arc there. And then there's what is known as gravitational weak lensing. When you can see arcs, that is known as strong lensing. But then there's places where outside here, these galaxy shapes are also distorted. But you can't see it with the naked eye. So you have to do a statistical analysis of the shapes of the galaxies to see a trend that they're all distorted in the same direction toward the center of the cluster. And so using weak lensing, we can actually map out how much dark matter is in this cluster, and that's what this blue stuff is. That's the distribution of dark matter within that structure. If dark matter exists, we don't know that dark matter is the only answer to this problem. It could be that gravity just works different at a scale of galaxies or larger in a way that we have yet to figure out. And there was one example of this that was invented by an Israeli astronomer called modified Newtonian dynamics. It's been modified over the years, and so the people that are advocates of dark matter and the people that are advocates of MOND argue incessantly. So here we go. we have all this evidence for dark matter. Really simple. At the scale of galaxies, nothing moves consistent with the speed of light. But if you add, consistent with the laws of physics. But if you add this stuff, this one solution solves every problem. That's why people like it better than other solutions. So what is dark energy? I know, math. Can't live without it, all right? So this guy here, young Albert, he wrote down this equation, or maybe it was Lemaitre or Friedman, and this equation describes how the universe behaves in time. So H is related to the expansion rate of the universe. All of this stuff is a constant. So you can think of it as like 7, right? Basically, ignore it. You see this factor here, A? That is the average distance between galaxies. So think about what happens in a universe that is expanding. In an expanding universe, A gets bigger with time. So if this thing right here, which is the density, the amount of stuff in the universe, is bigger, as the universe expands, this term gets smaller. After you make the denominator of a fraction bigger and bigger, the fraction gets smaller and smaller. So this one gets smaller faster than that one gets smaller, because this is to the third power, that's to the second power. So what does that mean? That means that if this starts off positive, it's going to get smaller faster than that, so eventually they're going to be equal. If K is positive, they're going to be equal at a certain point, and then this one is going to come to dominate. If K is 0, then so that means that the universe, the expansion rate is positive, and then it stops, and then it goes backwards. If K is 0, you just have positive expansion. If K is negative, you just have positive expansion, which is happening even faster, right? So scientists were trying to figure out, what is the fate of the universe? Is it going to expand forever, which is K equals 0 or K negative? Is it going to expand for a while, stop, and then go back, K positive, or what's going to happen? So they set about attempting to measure it. So there's a nice way to measure the size of the universe versus time. So what we have here, this blob in the middle, that is what we call the spectrum of a galaxy. These lines right here, those are references, so we know what these lines are, these dark lines in the spectrum. And if you look at these 2 dark lines right here, we see that for this galaxy, and then the next galaxy, they're shifted more, and then they're shifted more, and then they're shifted more, and then they're shifted more. That is the cosmological redshift of the universe. What does that mean? As light travels through the universe, between galaxies, space is expanding. So the light gets stretched out by the exact same amount that space expanded while the light was traveling through it. All right? So Edwin Hubble combined that measurement of light getting stretched out with measurements of the distances to galaxies and discovered that the universe itself is expanding. So basically, if you're a scientist, you plot your data and it all falls on the line, you just made a discovery. That's one of the laws of science. And so quite often people think that the cosmological expansion is like a Doppler shift, which is an apparent change in wavelength. It's not. It's a real stretching of the light. And Einstein also taught us that the shape of space-time, the curvature of space-time, is determined by the amount of stuff in space-time. So think about Earth. If you stand far away from Earth, Earth looks like a sphere. It has a global curvature that makes it a sphere. But if you're standing here in Hong Kong, oh, there's a mountain, there's an ocean basin, there's a lot of variation. It doesn't look like a sphere. Well, space is the same way. Around planets and stars, you have local curvature, but space itself has a global curvature, all right? And so we attempt to measure that global curvature, because you remember, that's one of the things that determines the fate of the universe. The curvature determines the fate of the universe. So here is a measurement of light that travels through the universe from 380,000 years after the universe began. So when we receive this light has been traveling to us for 13.5 billion years. And you see all these dots? We can predict what size they should be. And so, imagine they're traveling through space. If space is not curved, the light from one side of the dot is here, the light from the other side of the dot is there. If space is not curved, those two rays stay parallel forever. But if space is curved, then they'll either come together or go apart, as this slide shows, right? So here, if there's zero curvature, a flat universe, the spots appear to be the size we think they are. If space is positively curved, called a closed universe, where K is positive, which means the universe expands and then goes back down, the spots will appear bigger than we expect them to be. And if K is negative, they'll appear smaller. So all we have to do is measure the size of those spots. Uh-oh, where's my spot size? Okay, I didn't do it. So the other thing is, you know the Pythagorean theorem, a squared plus b squared equals c squared? That's what this is. Einstein taught us that it's not just a squared plus b squared. You know, we live in 3D, so it's a squared plus b squared plus c squared. But also, we live in space-time. So one of the consequences of our reality is that at all times, everything in the universe is moving at the speed of light. Can you feel it? You don't feel it? Get more streamlined. You don't feel it? Okay, well, we're not moving through space at the speed of light. We're moving through space-time at the speed of light. Every one of us, at all times. And so, what matters is, are you putting your speed through space or through time? So because we are all relatively at rest with one another, we are all moving through time at the speed of light. But if one of you were to take off going really fast through space, you necessarily must go more slowly through time. That's what Planet of the Apes is based on. That's what Interstellar is based on, right? It's called the twin paradox in physics. The faster you go through space, the more slowly you go through time. It's just like the Pythagorean theorem. Your speed through space squared plus your speed through time squared is equal to the speed of light squared. So if you're at rest in space, you're moving through time at the speed of light. But it's all relative. So space is also expanding, so we have to add this A factor in front of the space part, right? Like I showed you earlier. So how do you measure this? Well, nature provided us a nice little tool. When you look at the night sky, half of the stars that you see are not individual stars. They're double stars, all right? Two stars in orbit around each other. And usually those stars will have different masses. The more massive a star is, the faster it evolves. So stars have two main parts. Like if you take the sun, it has a core, which extends to about 25% of the radius, but contains 50% of the mass. That's where the fusion reaction is occurring. And then you have the envelope, which is the rest of the atmosphere, the other 75% of the radius, all right? When stars die, they throw off their envelope and the core is left over. And so a small star like the sun will become a white dwarf. And that's what's right there. And later, the partner star, as stars evolve, as they get older, they expand. So the sun today is bigger than it was yesterday. In fact, the expansion of the sun over the last 10 billion years or so means that the sun today is 20% brighter because it's bigger than it was when the Earth formed, okay? So when the star expands, it can fall into the gravitational influence of its partner star, and it'll start sucking mass off of it. And this is from a simulation. And if it sucks the mass off slowly, these white dwarf stars can only get to about 1.44 times the mass of the sun. And if they collect more mass than that, then nuclear reactions will once again start in the core of that white dwarf, and it'll blow itself apart and explode. And here's an image of exactly that. You have a galaxy here, and then you have the star explode. And when these stars explode, you're talking hundreds of thousands of stars in that galaxy. And that one exploding star is brighter than the hundreds of thousands of stars, hundreds of billions of stars in its galaxy. In fact, a single exploding star is brighter than all the other stars in the observable universe added together. All of the non-exploding stars in the universe added together, right? So what do? We find a supernova. Now, in truth, you have no idea where a star is going to explode in the universe. So what you do is you take images of galaxies through wide field telescopes, later take images of the same region, and then subtract one image from the other. Anything that changed is going to be left over. So here you have 3 weeks before, then you have the supernova go off, right? You can't really see much of a difference, but when you subtract this image from that image, there's something left over. That's the supernova. And so in astronomy, the most important and the most difficult problem is measuring distances. And so when we measure cosmological distances, we have two main tools. And they both have to do with how things appear as they become further away. So if you have a light of known luminosity, the further away that light goes, the dimmer it becomes. Twice as far away is 1/4 as bright. 3 times farther away, 1/9 as bright. 5 times farther away, 1/25 as bright, all right? And the thing about those particular stars, these guys right here, is that, remember I said they have a mass limit of 1.44 times the mass of the sun? Since they all explode at around the same mass, they all have very similar brightnesses. And to the extent that there is some variation, we can fix it. So you watch the star explode, it gets bright, and then it fades with time. These are days, all right? So it took about 50 days to go to maximum brightness, then about 100, another 50 to go down to near zero, right? And so you measure the brightness when it's at its brightest, and that's the one we know how to calibrate, and we can get the distance to that exploding star. And because light moves at the speed of light, if you know the distance, you know the amount of time it took for that light to travel to you. And then you look at the spectrum of the star. These are all, you take the light when it's at peak brightness, spread it out in wavelength, and this feature right here occurs at about 0.6 microns. But because of the expansion of the universe, if you look at it, if the universe is, bigger, 1.7 times, it doesn't occur at 0.6, it occurs at 1.6. So we see how much light got stretched while the light was traveling to us. And remember, the light stretches by the exact same amount that the universe expanded. So think about it. By measuring the brightness, you get time. By measuring the redshift, you get the size. Together, you get the size of the universe versus time. And so you can compare that measurement to if there is a closed universe, K is positive, a flat universe, K is 0, or K is negative. And that's what people were trying to figure out. Is it positive, 0, or negative? And the answer turned out to be none of the above. It turns out that space has an intrinsic curvature called, and Einstein had anticipated this for a bad reason. Here was the bad reason. This happens in science all the time. You make an observation or you do a calculation, you get an answer, and you say, I don't believe this answer because I know how the universe works, and it doesn't work that way. So Einstein was like, what? He wrote down his equations and found that it predicted a universe that's either expanding or contracting. He's like, what? I know the universe ain't expanding or contracting. I need to add something to fix that problem. And he added this thing right here that he called the cosmological constant. And a few years later, Edwin Hubble discovers that the universe is expanding, and he says that this is the biggest blunder of his career. And it took until 1998 for us to realize, no, Albert, you had it right all along. This is real. There are different types of ways to have dark energy, but it turns out that what we observe looks like it is exactly what Albert Einstein said it was. But the second we got this result, it created problems for us. Because the first one is, we can calculate what that value of that constant should be. From first principles of physics, we can calculate it. And when we calculate it, the answer is not exactly what we observe. It's off by a little bit. How much? That much. 10 to the 120. Here's the other problem. I told you that the universe is expanding. So what happens to the density of matter with time? It decreases, right? So since the cosmic microwave background radiation was created, the universe is 1,100 times bigger than it was then, right? So how does the volume change when the radius changes by 1,000? The volume changes by 1 billion, all right? So the density of matter has decreased by at least 1 billion times since the CMB. And if you look, that cosmological constant is constant. It has the same value. The mass energy density falls off a lot with time. Today, when we're measuring them, they're about equal. What's the probability of that? Impossible? Let me make it for you more graphically. Here's the situation today. 60 some odd percent dark energy, 30 some odd percent matter and dark matter combined. If you go back a little bit in the past, when the universe was half its size, it's matter dominated. Quarter its size, it's all dominated by matter. Go into the future a little bit, it's all dominated by dark energy. But yet, when we're here to observe it, they're about equal. We call that the cosmic coincidence. Unless there's something that makes it turn out to be equal. And there is one idea called a quintessence tracker model, but that's dead. It doesn't work. So, yikes. So here we are. We're in this situation. The laws of physics don't predict it. We don't know why it is. And after studying it, the particle physicists come up with all sorts of ideas for dark matter, and one by one, they've fallen. And so right now, we're left with one, this thing called an axion that's poorly motivated to exist. It's never been seen, but armies of scientists all over the world are studying the axion theoretically, and they're doing experiments to discover axion. But just like the supersymmetric particles before them and the machos before them, my prediction is that it's not going to pan out. So this is still a huge mystery. So basically, this is the good stuff, because we like to solve problems. We like to solve mysteries. And this has been the toughest mystery of all. Dark matter and dark energy today are still unknown. We know what effect they have on the universe. We observe that the effects are real, but today we still have no good ideas for what dark matter is in particular. Thank you very much. Questions?
Thank you so much.
Oh, let me say. Oh, by the way, in my culture,
Sorry.
If you enjoy the talk, it's customary to throw cash up to the stage.
It's not the culture here.
Not the culture here?
No, absolutely not. Thank you so much.
We call it making it rain.
All right. Originally, we expect giving like 60 minutes, 1 hour, 2 hours for Dr. Oluseyi to share a talk, but completely good because we can spend more time on discussion. Yeah. So now we will set a table, set 2 chairs on the stage so that Dr. Oluseyi can take a little bit a small rest here because yesterday he just arrived from the United States just yesterday night or afternoon. So
I swam here.
Oh really?
Yeah.
But he's still so energetic. So when he first arrived, I have a question. Oh, I thought you must be so tired, but it's not. So you can see he's really very energetic, and it seems he's just staying in Hong Kong for many time already, but he's actually just arrived yesterday. Thank you. So so now we can open floor for the questions. If you have any questions, you can raise your hand and our colleagues will give you a microphone. And if you are joining online, you can also share your question through the online platform so that I will speed out the questions. And if you want to ask in Chinese, you can also do that, and I will have to do the translation. So please.
Thank you, very dynamic talk. I'm kind of new and I don't quite understand a lot of it, so I ask a very simple question. As the universe is expanding, the space is expanding here and expand to here, and the light is traveling from here to here, when it expands, what happened to the light?
Yeah, it gets stretched by the same amount space is expanding while it travels through it. So it continues traveling, but its wavelengths get stretched out more and more and more. Yeah.
Because the wavelength is measured by the distance. And
that's right.
The origin get moved. But the light is still here.
Yeah.
So that gets stretched.
It's really getting stretched. Mm-hmm. Yeah.
Okay. So, but basically it's still, the travel is still here.
And so, you know, because the way expansion works, like imagine if I have a rubber band, and the rubber band is 1 meter long, and in 1 second I stretch it so it is 2 meters long.
Right.
If you're on one end and you look at the opposite end, you see the opposite end move away from you at 1 meter per second.
Right.
The center goes from 0.5 meter to 1 meter away. So the center moves at 0.5 meter per second. And the part right here next to where I'm holding it, it doesn't move hardly at all, right? So an evidence of stretching is that everything is moving away from you, and the rate at which they move away from you is proportional to the distance. But what you can imagine is the further and further you go in the distance, the rate of expansion increases more and more. So there are places that are sufficiently distant that the rate at which they're moving away from us exceeds the speed of light, right? So for some of them, we will get their light eventually, and then there's a horizon beyond which we would never receive their light. Yes, sir. You should stand on stage, and whoever raises their hand, you just throw the microphone to them.
So how long do you think it'll take for us to actually fully understand and find out what is the state? What is, because obviously we've got different states of matter, solids, liquids, gases, but what does it have its own state of matter at all? I mean, what we don't know, do we?
Man, it's really weird because if you do the problem in the opposite way, all right? Suppose you're a part of the dark universe. You're a being in a dark universe, and you see the gravitational effect from our universe. And you say to yourself, oh, I can think of a particle that could do it. It's the electron. Maybe all of that stuff is made up of the electron. You'd totally be off base because it's more complex, right? We have light, protons, neutrons, and electrons. And when we look at the dark universe, we're like, oh, it's the axion, right? What are the chances is one thing? You know what I mean? So it's such a difficult problem, and no one has really, thought of a way of, we thought of all these options. Oh, the laws, that's what theorists do. Who's a theorist in here? Where are my theorists? All right. So theorists, when the observations show or an experiment shows some new phenomena, the theorists get to work and they try to figure out everything that is consistent with the data, no matter how crazy it is. Because if they put forth 100 ideas and 99 of them are crap, people only pay attention to the one, right? It's like my career. Like, I failed so many more times than I've succeeded, but people only see the successes. So I think I'm a failure and everybody else thinks I'm a success. Lesson in life.
Okay, so I have a question from the online platform, a very interesting question. How dark energy gets its energy, or how is it created?
Well, here's the thing. If you look at, and I agree, there's a physics communicator online. It's a woman from Germany, Sabine Hassenfeder. Love her, because she always talks mad trash about the physicists. And she advocates this, and I also advocate the same perspective. Even though space has a intrinsic energy density, I don't think dark energy is stuff in space. If you look at the equations of general relativity, it shows up as what we call a free parameter of the model, just like the gravitational constant does. And what that means is that's just something in the universe that you have to measure. And what it appears to be in the equation is, if you remove everything from space, what is its intrinsic curvature of empty space? That's what dark matter is. If space is empty, it expands rapidly in the way that dark energy says it does. Now, but still, here is why we think that it has the value it does. We measure space to have zero curvature. And so when you put in the models of your theory for all the data, you can't fit the data. There's two things, right? So if we measure dark matter to be this percentage, matter to be that another percentage, and we know there's zero curvature, we know that the energy density of the stuff that has positive gravity and the stuff that has negative gravity must add up to give you zero curvature. So we know that matter plus dark matter is like 30%. So dark energy must be the other 70%, right? That one is kind of hand wavy, but the other way is that when you're fitting all these nice plots that we have in cosmology, you have certain parameters that you fit, and one of them is the energy density of dark energy. And that energy density still comes out to be 68%, right? So, right now, how could you possibly measure it? What it is, there's a parameter called W, which stands for it's a ratio of pressure and density, and it's called the equation of state of the universe. And so we measure W, and when we measure W, we get Einstein's cosmological constant. That's what tells us it's a cosmological constant. And so that means that it's something intrinsic to space-time. Now, energy, when you look at things fundamentally, we have a science called quantum mechanics. And one thing about quantum mechanics is that you have what are called quantum fluctuations. So imagine you have our glass of water. Oh, I messed up. Imagine it sat there for 1,000 years and it was perfectly stable, not moving. If you looked at the surface of that water microscopically, you see that it is moving, right? Well, the same thing is true of the fundamental contents of our universe. Everything that you call matter is really energy contained within a field. And those fields all fluctuate quantum mechanically. So everywhere in space around us, matter, antimatter particles are popping in and out of existence because of these fluctuations in these fields, right? We call them virtual particles. So space-time does the exact same thing. The phrase that we call for this energy in space-time, we talk about quantum foam, right? So there is a seething, but when you calculate what the energy density is, you find that it's off by 10 to the 120, right? So it's truly mysterious.
Right, so this fluctuation also related to vacuum energy. But vacuum energy is another concept. It's not dark energy, but it's quite different.
Right, yeah, like the Casimir effect energy. It's from these virtual particles, right? So you can make predictions of, if they exist, how could we see their effect in the real world? So Casimir came up with this idea called the Casimir effect. Once you confine things, like say for instance, I have a string that's infinitely long. I can put a wave of any wavelength on that string. Now, if I take a section of that string and put it on a musical instrument and hold it down in two places, only certain vibrations can exist on it now. If it's not held down in those two places, any vibration can exist on it. But once I hold it down, it now must play the same note over and over, right? So, how did I get there? What did you ask me?
Similar, the vacuum energy.
Oh, yeah.
The fluctuation in space that create particles.
When you put two conducting plates close together, now only certain wavelengths of particles can exist between those plates. Anything can exist outside. So you have more states possible outside than inside. So once they get sufficiently close together, you see this what appears to be an attractive force between the plates. And you can use the physics of the situation to calculate what the magnitude of that force would be, and we find that they match exactly. So the Casimir effect is direct evidence of this vacuum energy density.
So I think, ladies here, please, maybe a microphone.
Hi, I
Hello.
probably have the dumbest question. It's about the particles. So you were talking about how there are different particles. What I would like to know is, can you tell us a little bit more about like the properties of these particles and what are known knowns of the particles?
You asked me to solve the problem.
Okay.
We don't know the properties. All we know is they don't interact with light. They don't yes.
Okay, so we know we don't know that much, but
Yeah.
aside from, so all we know is that how it can bend light,
Gravitational effects. Yeah.
Do we know if there's just one type of particle?
Right, exactly. That's what I'm saying. We don't know that.
So
but we act as if we do.
Okay, so there might be multiple types of particles.
That's right. So the very first example is that there are these cosmological theories that require these things called supersymmetric particles. So that means that every lepton, which are like electrons and neutrinos, we divide the matter particles into two parts. There are the heavy particles, the hadrons, that we call quarks, that make up the protons and neutrons. And then there are the light particles that don't weigh much, the electron and neutrino. And they're completely different. But it's thought that at specific energies, every quark has a lepton partner, and every lepton has a quark partner, right? And so the supersymmetric partner of the proton is the sproton. The supersymmetric partner of the neutron is the sneutron. Of the electron, the selectron. Of the neutrino, the neutralino. Of the photon, the photino, right? Well, if they existed, CERN would have created them. They didn't show up. So supersymmetric particles are dead. But if that were the case, there would be multiple types of dark matter particles. But since they apparently do not exist, we're back to square one with the poorly motivated axion, which is one particle.
Yeah, and this was the main objective of the Large Hadron Collider. When it was built, they're trying to find the supersymmetry, the particle, but they didn't find any of them.
None.
Yeah. So, is it a question?
If dark energy keeps expanding, do you think that the universe will eventually explode?
Well, they call it the Big Rip. The idea is that right now, you can only see the effects of dark energy on scales about 100 million light years and greater, all right? And so the rate of expansion would increase. So where galaxies are, space does not expand. Where matter is, space does not expand. If anything, it contracts. So, I mean, we're only expanding from our food. We're not expanding from the universe, right? And so as the rate of expansion increases, then you start to see the effects of expansion at shorter and shorter scales. And so people think that eventually it'll pull the galaxies apart. Then it'll pull the stars apart. Then it'll start pulling matter apart in smaller scales until eventually it pulls space-time itself apart. And that's why they call it the Big Rip. I think the universe will somehow prevent that from happening. I don't know. It just doesn't sound physical to me. It's like infinities. There are things that pop up in our mathematics that I'm like, I don't see how like a singularity at the center of a black hole. That doesn't sound physical to me.
I learned that recently, I do not know if it's correct, the discovery of a galaxy. There's no dark matter.
Yeah.
I just want to know more.
Yeah, that happened. And there's been a few of them now. They find these dwarf galaxies that have no dark matter. And the crazy thing about that is that when you look at normal galaxies compared to dwarf galaxies tend to have a higher percentage of dark matter. So now you have these dwarf galaxies with no dark matter, and our theories of galaxy formation require dark matter to sort of be the superstructure that undergirds where the matter goes, right? But not only did that tell us that we didn't know what the heck we were talking about with galaxy formation, now we have the James Webb Space Telescope that's made it clear we don't know what we're talking about when it comes to how galaxies form. Because the amount of time it takes to form galaxies, the universe is doing it way faster than we thought possible, right? If you calculate either by small things colliding or big things collapsing, no way should you be able to form galaxies on a scale of like, it should take like 1 billion years. But we see galaxies that are well-formed, evolved galaxies, a few 100 million years after the start. So that's wild. We don't know what's going on. Yeah.
Okay, so I have a question. I don't know is really related with dark energy.
This sounds like a hard question.
Oh, nope. So, you know that we have a cosmological redshift, right?
Yeah.
So, for the energy of photon is given by its wavelength.
That's right.
So, for cosmological redshift, the energy is decreased, right?
That's right.
So, where does energy go?
Exactly. I just asked that I asked that same question in my last talk a couple hours ago. Yeah, and so the thing to note is that conservation of energy does not have to hold for the universe as a whole. Just like you can expand away faster than the speed of light, conservation of energy is sort of like when people say, oh, we only tend toward disorder, second law of thermodynamics. There are some disclaimers that go along with that phrase that we never say out loud. Right? So for the universe as a whole, it's fine. Another thing that happens is galaxies lose their kinetic energy. As the universe expands, it creates what is known as expansion drag. And they all come to rest relative to space-time, right? Where did their kinetic energy go? So the universe is truly sucking the energy out of everything. And you can experience that yourself. If you go out on a clear, cloudless night and it's cold, if you take an umbrella and hold it above yourself, you'll remain warmer because you put a barrier between yourself and space, and space is sucking the heat out of you. How do I know that? Because amateur astronomers know that. And the reason why amateur astronomers know that is when you take your telescope out at night and it gets cold, moisture will condense on your mirror. So to prevent that from happening, you put an umbrella over your telescope. Yeah,
I don't know that.
That's right. You learn
Really?
a lot of things talking to me.
It's very practical. We can always bring a telescope, go outside, and this is a really big problem.
The same umbrella you use to block the sun in the day, you can block space at night.
Okay, I will try that.
Yeah, it works.
Okay, great. So, any other questions? This gentleman, please.
Thanks so much. You mentioned about, this is a not less scientific question, but you mentioned your successes and failures, and you mentioned you left academia and came back. If you could share a little bit about your kind of journey, I'd be really interested to hear.
Oh man, yeah. So I'm a kid from the village. In the U.S., I'd say I'm from the country, right? So my father dropped out of school when he was 9 years old. All right. My mother dropped out of school when she was 16 and pregnant with my older sister. And as coincidence would have it, my mother's mother dropped out of school at 16 pregnant, and my older sister dropped out of school at 16 pregnant. So I'm not just the first person to get a college degree in my family, I'm the first person to graduate high school. So when I leave high school, I go to the military. I go to the U.S. Navy, right? Going to college, I didn't know what college was. I mean, I knew college existed, and I knew you went to college to be a doctor, a lawyer, a teacher, or an engineer, right? And so I didn't see a place for me because, like, engineer, I had no idea what that means, right? What the heck is an engineer? An attorney, isn't that evil, right? A teacher, that didn't seem that cool. And a doctor, at the time, to me, it was like becoming president. It's possible, but probably not likely, right? So I go to the Navy, and I leave the Navy, and my friends convinced me to go to college, all right? And the other thing is I'm from a criminal family. My dad, how do I say this? He was an importer. An entrepreneur, okay? And, you know, he passed away in 2010, but if he were alive, he would be really surprised to know that his business is now legal in several American states. But at the time, you know, it wasn't. You know, so I went into business with my dad at 9 years old. By the time I was 14, I had my own business. By the time I was 16, I was carrying a gun every day. My first cousins on my mother's side, these guys were early members of this American social club on the West Coast you may have heard of, the Crips. So they started robbing banks and murdering people. So 2 of the 3 ended up going to prison for, you know, a couple of decades. And that's what triggered my mother to move me to the country, to move me to the village, out of the cities, right? Because I was on the same path. And what happened is I go to college and I don't know what I'm going to major in. My buddies convinced me to go to college. I get out of the Navy and they're like, dude, what are you doing? You're too smart to be hanging out around here. You need to come to college. And I tell them what I tell you. Well, I don't see no place for me in college. They're like, man, we got a DJ crew. We know you're a musician. You can join us. You'll love it. And I'm like, yeah, I don't know. And they're like, oh, it's really chill, man. I'm like, yeah, I don't know. They're like, it's 5-to-1 female to male. I'm like, okay, right? So in the fall of 1986, I show up to Tougaloo College, not realizing I was supposed to apply first. Because they're a small college in Mississippi, they were accustomed to dealing with people like me, so they got me admitted. And the year was 1986. So what was happening in America at the time is that these things you see in movies, drive-by shootings were beginning, crack cocaine epidemic was beginning, right? So my father's business changed, and I found myself addicted at the age of 21, and I dropped out of college, all right? And it was such a violent time that I decided I don't want this life. I gotta change it. And so at midterms come, I have all Fs in my university degree. So I'm like, if I'm ever gonna do college, I have to drop out now, because if Fs show up on my transcript, there's no way I'll be able to get money for college anymore, right? So I drop out, and the only job I can get is as a janitor at the nearby hotel, the Ramada Renaissance. I'm making $4 an hour. If I make $100 in a week, I'm really lucky. So I have no food for money. So the way I would eat is I would show up at work, and then at the hotel at 3 p.m., and then I go walk the halls, because when people order room service, they put their tray outside their door, so I would eat people's leftovers. That's how I was living. And then my big break comes. A bellhop gets fired. Now, a bellhop gets tips, and sometimes they can make $100 in a day, and I'm barely making $100 a week. So this is my big break. So I'm like, I'm gonna apply for the bellhop job. And I don't get the bellhop job. So I think to myself, I can't go from janitor to bellhop? I'm going back to college, right? So I re-enroll in college, and I have to take a physics class because I knew I was gonna be technical. So you gotta take chemistry, biology, and physics. So I take my first physics class. Now, as luck would have it, when I was 10 years old and bored in the summer, I decided I was gonna read our family encyclopedias from A to Z. I make it to E, and I discover Albert Einstein and relativity, and I'm stuck. And so I started reading about Einstein and relativity, decided I'm gonna teach myself relativity, right? And I start doing it. And then these professors from a nearby university come by years later, right? I discovered Albert Einstein at 10. When I'm 16, these professors come and they tell us about this thing called science fairs. Now, it's the 80s and personal computers had just come out. And my girlfriend got a personal computer, a TRS-80, Radio Shack, right? So I taught myself, it came with a little booklet that tells you the name of the program language, BASIC. So I taught myself BASIC. So when these professors show up and they're like, oh, you guys should do the science fair, I think to myself, oh, I know what I'll do. I'll program all the effects of relativity. In like 1983 in Mississippi. So I win first place in physics in the Mississippi State Science Fair. That's a big thing, by the way. And they're like, you should go to college and become a physicist. But I didn't know what that was, so I went to the Navy. And so when I take this physics class, I discover that I had studied so much physics for fun as a kid. I never met a class I like. So in college, you don't have to attend class if you don't want to. So I never attended classes. So for physics, I could just show up for the exam, get 100, go back home, right? And so I'm like, okay, physics is my major. And then these professors, so the problem was, though, I was so poorly educated. So you guys, in America, some states have much better education systems than others. I attended the worst education state in the country, Mississippi, all right? And within Mississippi, when Mississippi evaluated all of its schools around 2000, 2001, 4 schools in the state were given a failing grade. 2 of the 4 were my middle school and my high school. So when I went to the Navy, I got into a program that turned enlisted people into officers. And the way they did it is they gave you a year of hardcore academic and military training. There were 2 math classes, the regular math class and the remedial math class. Guess which one I was in? You don't believe in me. I was in the remedial math class. And in that remedial math class, they took us from arithmetic through calculus in 1 year. I got kicked out of the Navy right after we completed algebra because I have atopic dermatitis, this skin thing, right? You're not allowed in the Navy with it. So I leave, and if I had not learned algebra in the Navy, I would not have survived at Tougaloo. But yet and still, my first 3 math classes, I got a C. After I came back and re-enlisted and realized I was going to be a physics major, I thought, well, if I'm going to do physics, I have to learn math well. So I okay, I'll become a math physics double major to force myself to learn math. And then I decided I'm going to do every problem in the calculus book so I can get better at math. So every night after dinner, me and this young woman, Francesca Wilkins, went to our science building. We literally did every problem in the calculus book. After doing that, before I did it, highest grade I got in math class, C. After doing that, the lowest grade I got in a math class, A. So if you look at my grade point average, it's like below 2.0, and then I start taking all math and physics, and it's like up by 4.0. And miraculously, I get accepted into Stanford University for my PhD program. And once I got there, for the next 4 years, they did all they could to kick me out. They were like, who let this guy in? Like, literally, I got the worst grades of my life my second quarter. My second quarter at Stanford, I took 3 midterm exams and got the lowest score on every test in every class. And I was convinced I wasn't smart enough. And this Nobel Prize winner, Doug Ostroff, he convinced me to stay. All right? So I stayed, and then I became like the smartest guy there, and the rest is history. So, but I tell you, it's funny because there's an exam you have to take called the qualifying exam. And I failed the qualifying exam the first time I took it. And I had to go talk to the chair of the committee, a guy named Bob Wagner. Bob Wagner, his PhD thesis was titled Synthesis of the Elements, just to give you a hint. So Bob says to me, right, when you take it, you get a second chance to take it, okay? So I talked to the other people who failed, and I said, what happened when you went to talk to Bob? He said, he just asked, why do you think you failed? And he was like, study hard next year. When I went, it was very different. He said to me, he goes, Hakeem, we looked at your situation, and we realized that you have 3 options. Option number 1, maybe graduate school is not for you, and you should drop out. Option number 2, maybe graduate school is for you, but just not here at Stanford, so you should transfer. Or option number 3, you can stay and take the test again next year. We strongly recommend you take one of the first 2 options. What are you gonna do? Take it again, right? So before I go to take it again, I go talk to the new department chair, the new chair of the committee, who happens to be Doug Asheroff, the guy who convinced me to stay. So I go talk to Doug and I say, hey, Doug, I'm about to take the exam again a second time. And I want to know how you guys are going to behave. Because when I arrived, you said that if I passed the qualifying exam and got mostly A's in the graduate courses, when I got there, I did 2 years of undergrad courses, right? That first year, terrible. After that, boom, my grades shoot up because now I'm used to the expectations, right? So I get mostly A's in the graduate courses. And Doug says this to me. We're friends. But here's what he says to me at the time. I said, I didn't pass the qualifying exam, but I did get mostly A's in the graduate courses. And yet you guys still asked me to leave. I don't understand. Doug said this to me. He goes, Hakeem, you're absolutely right. You did get mostly A's in the graduate classes. And we took that into consideration. And what we said to ourselves is, if this guy is getting A's in our graduate classes, what does that say about our graduate classes? So we now have instituted in-class exams in all our first-year graduate classes. So all our incoming first-year students will have you to thank for their in-class exams. Right? Now, I put I put Bob Wagner on my PhD committee on purpose so he could see the amazing work I did. But fast forward, so I defend my thesis in 1999. I leave, go to Silicon Valley. I come back to do dark energy and cosmology, and I attend the American Astronomical Society meeting in 2003, January. And I'm walking down the hallway, and I hear someone calling my name, Hakeem. And I turn around, it's Bob Wagner, the same guy who delivered "You Have 3 Choices" to me. He walks up to me, goes, Hakeem, you always were one of the smartest ones. Nothing succeeds like success, I tell you. So it was a tough climb, right? But I made it. Yeah, now I'm in Hong Kong.
Yeah, I will add a little. Yeah, thank you. I would like to add a little comment because physics is really difficult. It's really, really a hard subject. It requires lots of mathematics, lots of training. But Hakeem started at like 21 to receive a formal training.
24.
Yeah, so it's wonderful because like us in Hong Kong, we need to start training at very, primary school, secondary school, and then you want to pursue a career in physics and astronomy, it requires a lot of training.
Yeah,
so,
absolutely does.
So, well, I have a question. Do you have any advice for students in Hong Kong or in any other places for those who want to pursue a career in astronomy?
Yeah.
So do they really need to start training in an early stage or?
That would help. That would help. Like, for example, my son, so when he was a young boy, my mother says to me, I think he's smarter than you are. To which I replied, not in these exact same words, no, the hell he ain't. Why? Neither one of my parents graduated high school. His dad has a PhD in physics, right? That's what makes the big difference right there, right? So I was starting off behind, and he's got a big head start. So I teach him myself. So he completes Algebra 1 at 7 years old, Algebra 2 and Trig at 9, starts calculus at 10. He says to me in middle school, Dad, in math class, I feel like a god among peasants. And to which I reply, see, that's your problem. Then when he starts taking AP physics last year, he goes, I feel like I've been preparing for this my whole life. And then he's like, yeah, my favorite class is physics because I can just sleep. I don't have to even do anything, Yeah, so I'm just like, the more times you see something, the better you get at it, right? I don't care who you are. If you do stuff a lot, you're going to get good at it. So the difference between me is I was doing things for the first time in my 20s that my colleagues were doing when they were like 13, 14. But the thing about it is that when you're so far behind, sometimes you choose not to even try. It doesn't matter who's better than you at something today. if you apply yourself to it, like literally the amount of time it takes to become a world's expert at anything is like 1.5 to 2 years, right? If you have a problem to work on and you solve that problem, you're now the world's expert on this topic, right? So that's why realizing that, I go into things I've never done before, right? I went from doing solar physics to doing semiconductor physics to doing supernova cosmology to doing ion propulsion, and now I'm doing like heliophysics at, the interface between the sun and the interstellar medium, and big data, right? Survey science. Thank you. Is that a beer? No, you promised me earlier. What's the Hong Kong beer?
Normal beer.
Yeah, like if I go to South Africa, it's Castle Lager. If I go to Kenya, it's Tusker. What is it? Young Master?
Yeah, we have a beer called Guai Lo. It's like
Quite low. The good one, not the.
Oh, I like it.
Okay, quite low. Yeah.
Right.
Hi, Doctor. So thank you for this really good talk about the dark energy and dark matter. And somehow my son has this question for you, but I don't think it's too much related. But yeah.
So I know this is a bit of a weird question, but what's the point of the Big Bang if the universe is kind of getting ripped apart?
It's not. First off, dude, you are so well spoken to be whatever age you are. First off,
9.
yeah, so well spoken. It's not getting ripped apart now. We don't know that to be the case. All right. And then the other thing about the Big Bang is that when the data told us that that's how the universe started, nobody liked that idea. Nobody believed it. So the phrase the Big Bang was coined to make fun of the idea. It's like, what? The universe started with a Big Bang. That makes no sense. Yeah, but you just gotta, whatever the universe tells you is what you have to listen to, and it is what it is.
Thank you very much.
Thank you.
I have a question that is there anything outside our universe?
Yes. There's another well-spoken. What are you doing with the kids in Hong Kong? Yes, there is. So the book I'm writing right now, because it's online, I'm not going to tell you the title, but it goes through the various types of realities that exist. And two of them, one I call the contextual universe. That's the universe beyond our horizon. There's so far, there's places we can't see because the light has not yet had time to reach us, right? And so we don't know the makeup of we have this tiny fraction of the universe that we have access to. I'm convinced that the observable universe, well, most of us are convinced, is just a tiny, tiny like atom of the entire actual universe. But also, the data tells us that the universe began with this event that we call inflation, all right? And one consequence of inflation is that the universe is steadily popping out new universes. And it will do so forever, an infinity of universes, right? So we have no access to those, and we will never be able to access them. I don't know if that's good or bad, but it sounds pretty like, oh no.
So there are other universes outside the universe.
That's what the data is telling us. We haven't observed that there are other universes. We've observed that the data is consistent with inflation, and that the type of inflation that we see requires universe to pop up all over the place. But we only accept as true that which has been observed to be true. So even though the data is telling us that, we still can't say it's true. It's just the best fit to what we observe.
Mm-hmm.
Yes.
Do we know the age of the universe? And
Yes.
if we do, how do we know it?
Oh yeah. So there's different ways of doing it. One way is to just do the expansion backwards, the naive way. And the other way to do it is to be more careful about it, where you basically make the measurements of how much stuff there is with positive gravity, attractive, how much stuff there is with negative gravity, like dark energy, what is the equation of state of the universe, and then these weird parameters that, theta and stuff that don't make sense. and you fit all that data, and one thing that pops out is the age of the universe, and it's 13.8 billion years. Yes, sir.
I just want to get your opinion on this. So, you were talking about the age of the universe and all that, but just your opinion. How do you define nothing? Like, what came before nothing?
Yeah. So something is virtually nothing, right? So we have, the universe is deceptive. So, for example, we think matter is a thing. All right, matter is simply confined energy, right? If you look at the mass of a proton, and you'll hear, a proton is made up of 2 up quarks and a down quark. If you add up the masses of those 3 quarks, it's only 1% the mass of the proton. What's the other 99% of the mass? It's the energy of the gluons that are exchanged in the bonds to hold it together. All right, and so there's a mental experiment that you can do, which is called light in a, here's something, just think about what Albert Einstein did. Albert Einstein said, I have a chunk of metal. If I add something to it that has no mass, say heat, does the cup become heavier? Say, for example, this is all metal, and I make it really hot. What is it gonna do? It's gonna glow and emit light. Right? Turns red hot. So something is leaving it, but that something that leaves it has no mass. Does it become lighter in weight? And the answer in both cases is yes, it becomes heavier. Yes, it becomes lighter. So he never wrote until the 3rd paper, E equals MC squared. What he wrote was M equals E divided by C squared. Because he said, it's as if you either added a small amount of matter or subtracted a small amount of matter that's equal to the amount of energy that you added by heat or that left by light divided by the speed of light squared, right? I forgot your question. What was your question?
Before time.
Yeah. So that wasn't your exact question. But the inflationary model, the reason why new universes pop off, here's what I was getting at. The only thing that exists really are fields and energy, okay? So the energy that came into our universe came from a field that we call the inflaton field. And the nature of that field is that it's rapidly expanding. And the way it gives birth to universes is that in tiny little points within that field, it decides to stop that rapid expansion, right? So if you take 0, 33 zeros, 1, that fraction of a second, 10 to the minus 34th of a second, is how long it took for us to go from that inflationary stage to not inflating. And at the end of that, the energy, like for example, if I drop this, it's gonna take energy. First off, in most places of the universe, if I release this, what does it do? Most places in the universe is just empty space. In most places in the universe, if I release this, what does it do? It just hovers right there. But look at what happens here. Ah! It moved by itself, right? If I release this and it just hovered in the air, you probably freak out, right? You should freak out when it did that, right? Because in most places in the universe, it doesn't do that. But what's happening here is that energy in this field is getting transferred to this, and it's manifesting as kinetic energy, right? So when that inflaton field, when it rolls down and gives energy to our universe, that starts the universe expanding, it also puts energy into the fields that create matter, right? The lepton fields, the hadron fields, right? So that inflaton field continues that rapid expansion. That's why we can never have access to any of the other universes, is because by the time it pops off another universe, there's so much between us and that universe that we can't interact, right? So the only thing that exists is matter and fields, but that idea tells us that energy and fields pre-existed the existence of our universe. So time pre-existed the existence of our universe. There's time in our universe, there's time out of our universe. Yeah.
So, well, because the time is limited, but
No.
there's still many questions
In
from the floor.
America,
But
it's only 8:30 a.m.
yeah, we still have 12 hours.
Yeah.
Yes, that continue. Well, I have a question first. So it's a quiz. I think you don't know the answer of my questions.
A quiz?
Right. Do you know the Chinese word of universe? How do we translate universe in Chinese? Have you heard about it?
Egg.
No, we have two words to describe the universe in Chinese.
All egg.
Right. We say universe is space and time.
Oh, really?
Really, in Chinese, the universe,
wow.
the translation of universe, 宇宙, it means space and time.
Oh, wow.
So everything in space, everything in time is the universe.
Oh.
So in our idea, nothing before the universe. So
Right.
everything in the universe, we call it universe.
Well, that's the same way. We think that's how we've thought about it until yesterday, right? That's why it's one verse everything, and we thought all space and time. We used to say asking what happened before the universe is like asking what's north of the North Pole. It makes no sense. But now we know it actually does make sense. Yeah. Like the knowledge is growing so fast and so rapidly. You know, like they were giving away the Bible, like, oh, that book is out of date. It was written in 2015, right? A book written in 2020 about the universe is now out of date. We do not live in the same universe that people 100 years ago lived in. They didn't even know there were other galaxies yet.
Yeah, that's right.
Yeah.
So it's very interesting because all the knowledge we talk about today is just come in within this less than 100 years.
Yeah.
So within this 100 years, human really found many discoveries, changed everything that we knew. Even in the time of Albert Einstein, in the time of Newton, they don't know everything of this. So it's really powerful. The human.
Everybody in this room knows
things.
more than Einstein.
That's right. So I think it's time to have any last questions that you want to ask. Yeah, the last one. But actually, if even after the lecture, you can still come out to talk to Dr. Oluseyi to keep him here. So please.
I have two questions. You can decide which one you want to answer. So the first one is that I'm struggling to kind of understand the stretching and the curvature, as in, like, in my head, if you're curving something or stretching something, you're stretching into something or curving into something. So, like, what are you curving into? And then the second question is, what actually is energy?
Exactly. Those are like two super tough questions, but they're not.
Physics
right?
101.
Right, yeah. So what are we stretching into? So it's math. So in the math of the universe, we don't look at our universe as a 3D volume. We look at it as a 3D hypersurface. And so in the mathematics of surfaces, you don't require an extra dimension to curve into. The mathematics of the surface is all on that surface, right? So physically it's hard for us to imagine, but mathematically it's pretty straightforward that you don't require that higher dimension for those things to happen. So the other question was, what? Yeah, what is energy? That's a great, it's something that we all say, right? We have a poor definition. So energy realized we call work, all right? And before it's realized, it's sort of like the potential to realize something, right? The potential to make things happen. Without energy, nothing happens, right? I know it's unsatisfactory. I've not seen a satisfactory definition of energy, but that for me is as satisfactory as it gets, you know?
Okay, thank you so much.
Yay.
Thank you, Dr. Oluseyi. And here we have a little souvenir for Dr. Oluseyi. It's a Chinese star map. They're telling you about how the Chinese ancient people recognize the sky.
Dude, I love history stuff, and it's in English.
Yeah, both in
Oh, this is it's both. Oh, this is, you just melted my nerd heart.
It's by our former curator.
Oh, nice. Oh. Thank you. I appreciate that. Yes. Oh. Yeah, I did. Yeah. Oh, wait a minute. Oh, there it is. Yes. Thank you so much.
Thank you, Dr. Oluseyi, and thank you for coming, and thank you to the U.S. Consul General of Hong Kong and Macau to make this lecture successful.
Follow me on social media.
So the end of this lecture. Thank you so much. Thank you.